you use it, and there's one example citation in there. So for those of you doing primes in P, you've got some extra help there because I put the citation in. But that's basically how it works. You just get citations, you put them in that file, and you compile it a few times, and everything kind of hooks up the right way. Okay, and so LaTeX does all the work for you. So that you should have no problem. In fact, I would recommend you download the files, do a test run to make sure you can get all the citations working. If it's all working, you should get no errors at the end, and you should have a little one in your PDF file that links to the actual reference. So make sure you can do that, because if you're at the last minute trying to get things to compile, they'll take you universally finicky and things can go haywire. So check it now, so you can ask questions. So that's one thing. Let's see. So yeah, so I've also posted the date for final exam. It'll be in class on the 27th, which is basically the first day of finals week. Right? So we'll just have it in class there. Someone asked about sample questions. I will dig up, for example, the samples from last time, so you can at least take a look at that. We haven't typically had final exams in this class before, so there are not too many examples to work with, but that at least will give you some idea of the kinds of questions that might get asked. Yeah.
I think that week is very hectic because
Sure it is.
25th is when you expect the projects to come in,
Yes.
and 27th is when you're asking us to write the test.
Yes.
Why?
Well, partly because because of the spring semester has all these graduation deadlines coming up, and there are people who are graduating and need grades, and so things are done very quickly.
Okay.
So we're kind of constrained that we also have to be kind of on the ball to make sure the project reports are graded and the finals are graded and everything's all ready to go, so that we can push the grades out very quickly. And then not only do we want to push the grades out, we want to give you time to come and say, no, this was a mistake, before it all gets finalized. So the spring timeline is a bit more compressed than the fall timeline, where you put the grades out at the end of December. It's nothing terrible will happen even in January. Whereas here, if things change in a way that could affect someone's ability to graduate, that's a big problem. And so we have to. So and since I can't just say, okay, well for these 5 people, I'm going to grade them separately and for everyone else, the whole bill gets compressed. So it's not. That's not the answer necessarily you're looking for, but it's also yes. But I suspect that's why everyone is compressed. Not just this class, right? Every class, Zoom has.
But we had it on the 1st, right? The 1st was the day that we were supposed to have the final. 1st of what is it?
Well, the finals week actually starts in a weird way, right? It starts basically from Wednesday and goes till the next Wednesday.
Yeah. So for our class, it was supposed to be on the 1st of May, from 10:30 to 12:30. That was what it is as per the schedule.
I thought so. Okay, so I'm a bit confused then, because as far as I thought, the only way to do this physical class is to have it in class itself.
No, there's a final exam date.
Okay, because I actually asked a bunch of people about this, and everyone said,
No, there is a final exam date, because if you look at the final exam schedule that's given on the website there on CIS, so it will give you a date for this class. It's on the 1st of May, 10:30 to 12:30.
Let me look into this. Okay.
If you could please
no
make
promises. Don't get excited. I will look into it. That
Yes.
doesn't mean I will.
Yeah.
So, one of 3 things can happen. Either I will not change it at all, or I would like to change it, but for other reasons I can't, or I'll change it. So, you have a 1/3 chance of this working out. So
Whatever,
okay,
I take
fine.
that chance. So.
Good, okay. I will look into it. Any other things before I get into the lecture? Yes?
Do you have any idea what the due date for homework 6 is going to be?
Yes, it's going to be a short homework. It's not going to be a long one. And therefore, it's going to be a shorter time window.
Cool.
Also, because we won't have time to finish the grading for the homework before the next one comes. Because we don't want to have like 5 different things piling on us for grading. So, it will probably be released tomorrow.
Cool.
Okay.
And it'll be due next week, and it'll be short. So, don't panic. And it'll be on approximations. And again, there's always the option, since we're going to drop one of the 6, right? If you suddenly feel like this is the one you need to drop, there's always that possibility.
Are they all weighted equally?
Yeah. This will be a smaller one, but it's still, if you can do well on this one, then that's fine. Okay. I will also, so again, there are some of you, not many, who are registered in 5150, and the most of you are registered in 6150. What I've tended to do in the past, when this has been cross-listed, is do everything together, but then do the grading separately. Okay, just for whatever reason. So I have to check how many people are actually in 5150. If there are like 2 people, then it's going to be hard to sort of do separate grading. But that's roughly, I think it's more than 2, but it may be less than 10. So and so keep that in mind. For most of you, this will make no difference because you'll be in a larger group.
Final exam are ready in the weekends?
No. No. that would be rather cruel, even for me. Yeah, no. This will be handwritten. So please try to make things legible. Don't cryptographically encode your answer so it can be encoded the way you want it when you come and argue with me later. So yeah, so you'll be doing handwritten. Yeah, no. That would be bad. Even I can't write it that fast. Okay, let's continue. So last time, after looking at a number of examples of how to approximate a problem, we came up against the traveling salesperson problem, one of these problems where it turned out we couldn't do anything at all. Any approximation for this problem was impossible, or rather more precisely, any approximation for this problem would lead us to show that P is equal to NP, or approximating this problem to any factor is NP hard. Right? It's kind of annoying. This problem is NP hard already. Now you're saying approximating to any factor is NP hard as well. And it turns out that the reduction, if you recall, we said, okay, we'll reduce Hamilton. We'll reduce Hamiltonian path to the traveling salesperson problem. And we basically said that if you can do any Fn approximation for some computable Fn in polynomial time, you can get an exact answer to the Hamiltonian path, therefore giving what we call a gap reduction. Right? So the Hamiltonian path problem was a problem where you either had a yes answer or a no answer. And this was blown up to a TSP cost of very big or small. And so any approximation algorithm that could distinguish between these two cases, right, would give me an answer to the Hamiltonian path problem. And this is typically what's called a gap reduction. So you're taking a gap and you're blowing it up. So being able to approximate a problem allows you to do something even better. And not surprisingly, you can chain these reductions together as well now. Now that we know that some problem cannot be approximated to within some factor, you can take some other problem and then show that can't be approximated to within a factor, and so on and so forth. So once you have these initial gaps, lots of things happen. And now this was not the first gap that was shown. Actually, I'm not sure when this gap was shown, but there were some very nice gaps that were shown in the early 90s, and there's a whole wonderful set of discussions we could have about that as well, on these things called probabilistically checkable proofs and the relationship to approximation. But that's another story for another day, another class. But what I want to show you today is that these kinds of results, even though they're negative results, saying that you cannot approximate this problem to any degree possible, don't actually make the situation hopeless. Because it turns out that by observing the problem very carefully and applying a little bit of extra structure to it, putting some extra information in the problem, you can do a lot better. And so let me explain what's going on here. So if you recall in the way we constructed this instance of the traveling salesperson problem, what we said was that you take an edge, any pair of vertices, if there's an edge between them in the original graph, you put an edge here with weight 1, and if not, you put another edge but with weight very high, right? So what would this look like? If you took a particular example of a graph, so let's say I have a graph that looked like this, okay? Then when I convert this to the instance of the traveling salesperson problem, I would first complete the triangle. I would have all edges, and I would put a 1 here because there's an edge there. I'd put a 1 here because there's an edge there. And I'd put some very large number, f of n, here to capture the idea that I don't want to approximate this to within f of n. Okay? And I would claim these are the distances I want to travel. And now I want to look at this example here. This example is basically saying that if I went straight from here to here, it cost me f of n distance. But if I took a detour along something else, it cost me 2. Now, I don't know about you, but there aren't many places out here you can find where this would happen. Usually a detour takes you longer. It doesn't take you less, does it? So even though we are able to construct a reduction from Hamiltonian path to the traveling salesperson problem, we are doing so by putting in distances that are not realistic in some sense. They don't capture actual distances. And since we are saying, oh, we want to maybe do a traveling salesperson tour in Salt Lake City or in the country as a whole, maybe the fact that we use these bizarre distances is what's making the problem hard, and if we didn't allow that, it would be easier. We don't know this, but it's possible. And for many problems, this kind of observation is what leads to a problem suddenly getting an easier solution. You say, well, maybe let me assume a bit more. So let me define another problem, which I'll call metric DSP. It's the same setup as before. I'm given a set of nodes, V, and a distance function from all pairs of nodes to R, just like before, but with one extra caveat, that this distance function is what is called a metric. So have we discussed metrics in the class before? A formal definition of a metric? I mean, the word is very commonly used. You probably heard the word, but I'm using it in a very specific way here. And the specific way I'm using it in is the following, that this distance function must satisfy certain properties. Here's a simple property it must satisfy. Distance to itself is 0. Yeah. In fact, let's ask for a stronger property, that dxy is equal to 0 means x is equal to y. So it's a bit stronger than that. Right? This is saying if two things have the same distance, they must be the same. The second property also is very simple. It's a no one-way street property. So we had that in the original traveling salesperson problem. We didn't distinguish between source and destination. That was still fine, right? And even this property was there implicitly, that the distance to yourself is 0. It's the third property that we did not have before. And this is the one, the magic property that makes all the difference. So I'm going to write it first and I'll draw a picture for it. This property here is called the triangle inequality. And it's the thing that defines a metric. A distance function is a metric basically because of this. And to get some intuition for what this is, you could think of this as the no shortcut rule. So if you draw a picture, if I draw my x, y, and z, I have x, y, and z. What this inequality is saying is that no matter what x, y, and z are, the distance to go from x to z by taking a long route is more than the distance to go directly. So this is a very natural thing, right? You'd expect this. Okay. You know, we want it to be the case that going somewhere directly is better. So that's what I mean that shortcuts are good. Right? Not no shortcuts. Shortcuts are good. Right? And now immediately our reduction breaks because we no longer have that property except for f of n is equal to 2. The minute you put f of n equal to 3, that property is not true anymore. And if you go back to our reduction for the hardness of the traveling salesperson problem, and you put f of n equal to 2, you find that the approximation limiting you see is very small. There is no real limit on what you can approximate. It's just basically distinguishing between n minus 1 and n. So once we require that the distance satisfy this natural shortcuts are good rule, we find that there is no longer a block on our ability to potentially approximate the traveling salesperson. Which means we can now try to design an actual algorithm. Okay? So do you see the change we've made? We've changed the problem by requiring more information, requiring more structure. That the input to the TSP must have the nodes and the distances, but the distance must satisfy these three properties. Then make it a metric, and hence the name is called the metric TSP. This is a special case of the general TSP. And needless to say, this problem is also NP hard. Why? Well, actually it takes a lot to prove this, but you can prove that's also NP hard. Well, the same reason actually. Because you can take the same construction from Hamiltonian path, and you can distinguish between a path of length n minus 1 and a path of length n by using this trick here. So if you could solve the TSP, you could solve that. But we no longer have a limit on how we can approximate, and so that's what we want to look at. Okay? Any questions so far? Yes?
So after this definition, you cannot change that problem if
f of n is more than 2. If f of n is 2, then I have a 1 plus 1, 2, it all works. If I put f of n is 3, then I have an example where I have a 1 and a 1 and a 3, and that violates this inequality. So I can no longer construct a valid instance of metric TSP for f of n more than 2. And since I can no longer construct an instance for f of n more than 2, I don't have this big approximation f of n more 1 anymore. My gap breaks. So now this means that maybe this problem is a little bit easier. maybe I can do better. That's my hoping. Yes.
Are you allowing for negative
No.
edge distances?
No, we're not allowed. Again, negative distances, you might end up breaking one of these things. Right? Because you could go and then have a negative distance, and then the shortcut will actually be longer. So no, all distances are possible. In fact, that's a good point. Yes.
Does it mean that we can no longer reduce Hamiltonian path to traveler's telescope?
We can reduce it. And so let me do the reduction. The reduction works the same way as before. So again, if you have, remember our reduction said, take your graph, right? Replace every edge in the graph by a path of length, by an edge of length of weight 1, distance 1. Replace every non-edge by an edge of distance 2. That's all you can do. Okay, so this will look like, okay? That's all you're allowed to do. This satisfies the triangle inequality. But now, look at the way what we said was, suppose you have a traveling salesperson tour in this graph that uses only edges from the original graph. Then the length right? And if the TSP must use some non-edge, then the length will be n. Because you'll have to use at least one edge of length 2 instead of using an edge of length 1, and therefore you'll have one more extra. So TSP length n implies no Hamiltonian path. So we can still use the reduction, but now our gap is between n and n minus 1. That doesn't give us an approximation guarantee. Because the difference between n and n minus 1 is not a multiplicative gap, it's an additive gap. As n goes to infinity, the ratio becomes 1. So you can't conclude that there's an actual, so if I were to say that any, I don't know, 2 approximation to TSP would give a solution to Hamiltonian path, that's not true. Because the difference between the good and the bad answer is only just 1, n minus 1 to n. A factor 2 algorithm, which is very rough, will not be able to tell between these two things. It can't distinguish a TSP of length n minus 1 from a TSP of length n. It might just say, oh, the answer is 2n. It could be either of these two things. So that's the key. The reason why the reduction worked earlier was that we create this huge gap between n and f of n. Here I can't do that anymore because I have this metric constraint. So while I can still prove NP hardness, this itself is a proof of NP hardness, I can't prove approximation hardness, which is good news, because now I can come up with an algorithm. Does that answer your question? Okay, all right. So let's try to come up with an algorithm. And as before, as always, the key is to find a good number. Some number that is always less than or equal to the traveling salesperson tour cost. One way to think about this is to say the answer we get is a path, right? So I have my graph and my answer is some path in the graph whose cost is the total sum of all the edges on it, right? That's the definition of the cost of the path. Now there's one thing that a path also is. A path is a tree. Every path is a special kind of tree, right? It's a tree with, just all vertices of degree 2, except for the 2 endpoints. So suppose we instead, in the same graph, instead of computing a path, computed a tree. That happened to also touch all the nodes. Now, of course, this is no good as a tour. But it's still something that's path-like. And in particular, the cost of the best tree has to be less than the cost of the best path. Because every path is a tree. Okay, so this is the TSP. And this is the best tree. We know that Yes? Where we again measure the cost of the tree the same, we add up all the length of the edges. So you see what I just did here? I said every solution we want is a path, but every path is a tree. So if you construct a tree instead, its cost must be less than equal to the cost of the best path. Because if it's not, then why isn't this path the best tree? That make sense? Where am I going with this? The whole point of defining a lower bound is the lower bound is somewhat easier. So now I'm saying, okay, I don't want the best path going through all the vertices. I want the best tree that touches all the vertices. Or I want the best tree that spans all the vertices. Where have we heard this before? The best cost tree that spans all the vertices. There's a name for this.
Minimum spanning tree.
Minimum spanning tree.
Yeah.
Have we not seen the minimum spanning tree before? We have. It's actually a very easy problem to solve. This is the minimum spanning tree. And this is great. We know how to do this. Run Kruskal's or Prims or whatever you want. So the minimum spanning tree in a graph, in a complete graph with weights on edges, is a lower bound on the length of the best traveling salesperson tool. So we've got part one. The approximation dance is a two-step dance. First, find the lower bound, and then design algorithm that use the lower bound. We've got the lower bound, the spanning tree. How do we get an algorithm out of this? How do we get a tour? We want a tour. We don't want this tree thing. It's going to keep repeating stuff. But do you understand the first part so far? Do we all see this? That we can easily compute a lower bound on the tree, on the path, by computing the minimum spanning tree. Okay. So what do you do next? We look at our tree. Here's something you can do on a tree. So let's take any tree. This is not just having to find any tree I want. Let's take any tree. Okay. I'm going to walk down the tree and walk back along it. Okay, so I'm going to follow the tree down. I'm going to do basically, you can think of this as a prefix, a pre-order sort of traversal of the tree. Okay, so I'm going to come down, go back up. Okay, imagine me walking along this way. Have I visited every node in the graph? Have I done it exactly once? No. But remember also that there's a way to get directly from any node to any other node, because this is a complete graph. So suppose I went down, let's see. Okay. So suppose I went down, okay, let me label the nodes. Okay, and let me write out the sequence in which I visit them. So I did A, B, C, D. No, sorry. Let me do this again. I did A, B, C, B, D, E, D, B, A, F, G, F, H, I, H, F, A. Right? This is the order in which I traversed all the nodes in the. Now I went to A to B to C. Now C is saying, okay, go straight to B. But I've already been to B before. I don't have to go to B again. Maybe I should just go to the next one on the list, which is D. Okay? So what I'm going to do is, I'm going to shortcut. Instead of going from C to B to back to D, I'm going to go straight to D. can always do that, right? Yes?
Why do we need the last HFA?
Pardon me?
Why do we need the last HFA? Because you already visited them.
We don't. You were right.
And
H and F.
Uh,
You end at I.
oh, I'm sorry. Yeah, you're right. You don't need all of them. So we went to B already, so we said, well, just go straight to D across. Okay? Now I go along to D, to E. I don't need to go back to D again. I don't need to go back to B again. I don't need to go back to A again. I can go straight to F. So from E, I just go straight to F. From F I go to G, and G goes straight to H. Right? If I now write down my new sequence, it's going to look like is this a valid tour? Is a valid traveling salesperson tour? It is, right? I visited every node exactly once. So now the question is, I took my original spanning tree. I did this for this red path. I made short circuited to find the green path. What is my cost? What is the cost of this tour? Can I somehow link the cost of this tour to the cost of the spanning tree? Because if I can then relate the cost of my solution to the cost of the lower bound, I have a hope of proving approximation. Right? This is the second step of the approximation game. We first came with the lower bound, but now we need to relate our algorithm score to the score of the lower bound. Let us look at the red set of edges. There's a very simple formula to relate the sum of the red edge lengths to the sum of the white edge lengths. Can you see it? What have I done to go from the white edges to the red edges? So look at every white edge and look at every red edge and pretend I didn't actually delete those last few there. But even if you did. So what can you say about the red and the white edges? It's at most a double, right? So the red edges, the red edges is less than equal to 2 times the white edges, right? Okay. What about the green path? When I did my short circuit from C to D, I replaced, what do? I replace CB plus BD by CD. Can we say anything about the resulting cost of doing so? What can we say about this? Let's look at this more carefully. We're replacing CB plus BD by CD. Oh,
Triangular.
You're also replacing VAN.
not yet. Just first thing. Just for now, right? Yes?
Triangular inequality.
Triangle equality. What can we say then?
CB plus BD is less than equal to.
Other
Greater than equal to.
greater than equal to, right? Because by fiat, we have said, no, our distance function must satisfy this property. Short circuits are a good thing. We just short circuited the path from C to D. So short circuiting cannot increase our cost. It might keep it the same or reduce it, but it can never increase the cost. So all the short circuits we've done, and it doesn't matter whether it's just two. Just by induction, you can realize that the short circuit from E to F is going to be less than the sum of these things. Because you can apply it inductively, right? It's okay, this distance is less than this plus this, then this distance is less than this plus this, and so on. Right? So it's not hard to see that this short circuit is going to be less than taking all of these paths here. So every time we do the green short circuit, we have at most kept the cost the same or possibly reduced it. Which means that the green is less than equal to the red. Right? Because of the triangle inequality. See, that's where our assumption came and helped us. So what can we conclude here? We can conclude now from this that the green, oops. Have you ever done these psychology experiments where they make you read words, like the word red was written in green and the word yellow was written in blue? And suddenly your brain has a hard time trying to figure out what exactly what you're looking at versus what you're trying to say. It's an interesting test. So green is less than equal to 2 times white. Right? We just proved this now from those 2 equations. But what is white? White is the MST cost. In fact, you can rewrite this as algorithm is less than 2 times MST. Because the white is just the MST cost. And the algorithm cost is what we just produced in green. Which means that, if we go back to the previous slide, we said that MST was less than equal to opt. We said algorithm is less than equal to 2 times MST. Therefore, algorithm is less than equal to 2 times opt. And we have a 2 approximation to the metric TSP. So that triangle inequality just gave us a bit of help. Any questions? Yeah.
Can you remind me very quickly how to get a minimum Spanish?
The algorithm?
Yeah, just
Oh, you'll remember because it'll be on the final. You, for example, Kruskal's algorithm will say, take all the edges in your graph and sort them from least to highest. Keep taking the cheapest edges as long as you don't create a cycle. If you create a cycle, reject that edge, get the next one, and keep doing this till you've touched all the vertices. So, n log n time algorithm. Yes?
So what about the alternative formulation of, I guess it's probably not the traveling sales problem, but where you want to visit every node minimum cost, but you don't care that you visit each one once. So then you've already baked in.
So you just want to visit every node?
Yes.
So a spanning tree will do that. So a spanning tree will do that.
But it's still packed.
So you want a path.
So I feel like this is equivalent to, instead of making the metric assumption, you can just say, I want, instead of to visit every node exactly once, I'm okay visiting a node multiple times.
But you want to find the minimum cost?
Yeah.
But the minimum cost solution to visiting to visiting all nodes, where it's okay to visit a node more than once, that answer will always be a solution where you visit a node exactly once. Because if you ever visit a node more than once,
Not in the case where the
I see. Because you could.
And I feel like this is equivalent to saying, oh, but I could, instead of taking the long route, I could have gone back to this node and gone another place. That's the triangle inequality. At worst, going directly, I could have gone back to the other node.
Sure. Yeah. So if you have that particular problem, you could solve it directly through this. Except that what you will get is a solution that's always twice the minimum spanning tree cost. Right? So if you say, I want to just find some path, that'll be exactly twice the minimum spanning tree cost because you're not doing the short circuits at that point. So why wouldn't you do the short circuits? That's always going to help you. In other words, I'm saying that it's not clear that this gives you an exact answer to that formulation problem. It might give definitely even a good approximation, but it might not give you an exact answer. You'll require different proof to prove that's an exact answer. That's what I'm saying. That's my thing. Yes?
So could you remind me, why were we able to turn this into a complete tree? Or, sorry, a complete graph?
Not why were we, why did we, I guess.
Why did we?
Because the definition of the traveling salesperson problem is that you're given a complete tree.
Okay.
You're given distance between every pair. That's the definition of the problem. If you think of it like a graph with missing edges, that's not the definition of the problem.
Okay.
The definition is you can go from anywhere to anywhere. Right? You just have to find a good way to do it.
But if you think of it as a graph with missing edges, you can always, as long as it's connected, put a length of the edge there equal to the shortest path through the graph. So,
Right. Of course, in reality, you're not going to build roads, but this is the way the problem is defined. It's set out like that. Yeah.
Okay.
Yeah. That's why you can always do these jumps, these teleportations across. Yes.
You use triangles inequality for using CD or removing B for the first.
Yes.
But how can you use the triangle for for E, D, B, A, and F.
Okay, so I want to show that if I go from E, what is it? E, B, D, A, F. Okay. E, B, D, A, F, it's quicker to go this way, right? Okay, so we can write this out as a series of inequalities. E to D is less than or equal to EB plus BD, right? D to F is less than or equal to DA plus AF. E to F is less than or equal to ED plus DF. Therefore, EF is less than or equal to EB plus BD plus DA plus AF. You just change the inequalities. All right, yes.
You decide to, where do you decide to jump? You decide to jump to the
Next unvisited one.
unvisited one.
Right. Because that's, you don't want to repeat. Okay. So it turns out you can do even better than this. That while this two approximation is a little clever, you can be even more clever by observing what exactly you're doing. Let me rewrite this algorithm in a slightly different way. Okay? What's going on here is the following. You're taking the spanning tree and you're computing an Euler tour of the tree. So what's an Euler tour? An Euler tour is a tour that visits every edge exactly once. Now, of course, you're not doing that here, but you're augmenting the graph to make it Eulerian, so that in this new graph you can visit every edge exactly once, and then you're short-circuiting. So if you think of what this algorithm is doing, it's saying, step 1, compute MST. Step 2, make it Eulerian. Make the graph Eulerian, that means you can traverse every edge exactly once. Step 3, short circuit. And you're done. So this is the lower bound. This is the short circuiting. So the final cost is less than or equal to the Eulerian graph cost. And the MST to Euler cost is what we do by doubling. We double the edges in the graph to make it Eulerian. Because once it's Eulerian, you can traverse the whole thing. And so this is where the factor 2 comes in. The factor 2 in the approximation comes to the fact that in order to make the graph Eulerian, you just double it. You double every edge. Because now every vertex is even degree, and a graph is Eulerian if and only if every vertex is even degree. Okay? Is there a better way to make it Eulerian? That's the question. And it turns out there is. Here's the idea. Let's look at our minimum spanning tree again just before. So we have the minimum spanning tree. Okay, so we drew a tree here. Right? This is a well-known fact in any graph. The number of odd degree nodes are even. There are, again, an even number of odd degree nodes. Let's see how many odd degree nodes are here. This one has odd degree. This one is odd degree. This one, this one, this one, and this one. And this one, and this one. 1, 2, 3, 4, 5, 6, 7, 8. Now, this is a very elementary fact in graphs. The reason the number of odd degree nodes is even is because the total number of edges is, the total degree of the graph is an even number. It's twice the number of edges. So if you have a bunch of things that sum up to an even number, then the odd things in there have to be an even number as well. Otherwise, you would have an odd number again. So, why is this important? It's important if you think back to the definition to the characterization of an Eulerian graph. A graph is Eulerian if and only if all vertices have an even degree. Because then if all vertices have even degree, whenever you go on, you can come out essentially. So you can traverse all the edges in the graph. But here, in our spanning tree, we have odd degree nodes. We are not Eulerian. To fix that, somehow we need to make all these odd degree nodes even degree. Thankfully, there are an even number of them, which means you could pair them up in some way. For example, you could pair them up like pair up these two, pair up these two, pair up these two, and pair up these two. Now if you count, every vertex has even degree. And this graph admits an Eulerian tour. We would be able to complete step 2. So rather than adding just doubling the number of edges, we've added only these green edges. And so the question is this any better than just double? Right? Well, here's the thing. What can you say about this set of green edges? They form a very special structure that we've seen before. Huh? They don't form a triangle. None of these edges touch each other, which is also a clue. Yes?
Matching.
They form a matching. They form a matching on the odd degree nodes. They're a disjoint collection of edges that pair up all the odd degree nodes. They form a matching. So basically, we have an MST union, oops. Okay. This is in contrast to what we did before, where we had MST, right? Because we just doubled all the edges before. And so the question is this, what is the size of this object? Now we know the MST is less than or equal to the size of the optimal traveling salesperson tour. Can we say something about a matching? Let's assume that our graph is an even number of nodes. Doesn't really matter, it just makes the reasoning a little bit easier. Let's look at our path, our optimal tour. Okay, so let's look at our optimal tour. Okay? Now let me do something funny here. Let me color every alternate edge green. What can I say about this? If you look at the set of green edges, what special property do they have? What do they look like to you? They're disjoint from each other. Therefore, a disjoint collection of edges is a matching. Look at the pink edges. What are they? They're matching too, right? In other words, the optimal traveling salesman tour is equal to right? Yes? Therefore, right? If it's a sum of two things. One of them is bigger, one of them is smaller. So one of them is less than or equal to half of opt. They can't both be more, right? And therefore, if in fact the matching we constructed, the green matching on the odd degree vertex, was a minimum cost matching, the matching with minimum cost for the edges, then we can now say that this matching is less than or equal to opt divided by 2. And therefore, the size of this new Eulerian graph, remember our old Eulerian graph, we said was less than or equal to 2 times opt. This new Eulerian graph is less than or equal to 3 over 2 times opt. And the rest of the argument works the same way. Now you have an Eulerian graph, find a Tour, short circuit it. Its cost is at most the cost of the Eulerian graph, and that's 3 over 2 times opt. You have an algorithm that is a 3 over 2 approximation. This is called the algorithm by Christofides. This is from 1975 or so. To this day, in this general case, this is the best known result we have for DSP. We don't know if we can do any better. This is almost 50, 45 years old. 40. And so all we did was construct lower bounds. We had the MST, which was a lower bound. We had the matching, which was a lower bound. And we put them together in this very clever way. This is not something that you can apply as a standard trick, the whole MST matching dance here. But the idea of looking for lower bounds and then relating your solution to lower bound is, of course, a standard trick we've been using over and over again. And that's how just adding a little bit of structure to our problem, this triangle inequality, allows us to do tremendously better. Questions? Yes.
So what path was this path again that you're showing here
It was the optimal solution.
to TSP?
So again, we're reasoning about this thing we don't actually have. But we're saying, well, if it exists, then it must have these properties. Just like before we said the optimal path is a path and therefore is a tree, and then we can do the same. So we start off with no structure on the TSP, and we got nothing. Then we add a metric structure to the TSP, and we got something more. You could say, no. This metric structure is all well and good, but I'm actually driving around. These are points in the plane, right? There's a direct path, and let's say it's an open field, and you're going to hit a bunch of waypoints. You can go straight to any point. You have an actual distance, a Euclidean distance between things. Can you do even better? So if we tabulate now where we stand. So for TSP, general case, nothing. Metric case, you can get 1.5, 3 over 2. Case when metric equals shortest path in unweighted graph. So it's a very special case of the metric. You can get 1.4. These results came out a few years ago. And if metric is Euclidean, that means you're just looking at, you have points in the plane, just looking at shortest path. You can do something that we have not seen before. So what does this mean? This means that you can get an arbitrarily good approximation. Okay? No matter what error you want, I will give you an algorithm that will give you that error. You want 10% error? I'll give you. You want 1% error? I'll give you. You want 0.1% error? I'll give you. You want 0 error? No, I can't give you. Effectively, the algorithm here, the running time of this algorithm is basically a function of n and the error parameter, and it depends on it inversely, which is why you can't set it equal to 0. So it's a very complex function of both the size of the input and the error parameter, but you can do it. And we've never seen such a system before. This is a very complicated algorithm. I'm not going to explain it to you here. But the name of such a thing is called a p-TUS for polynomial time approximation scheme. It's a scheme because it's not a single algorithm. You first have to tell me what epsilon is, and I'll design my algorithm accordingly. So for every epsilon, the algorithm will look a little bit different. Okay. But for each epsilon, you can get a bound that runs in polynomial time in n and whatever epsilon and gives you the desired approximation. So you can get arbitrarily close to the exact answer without quite getting there. And this is in some sense the best possible world for an NP-hard problem. If you can't solve it exactly, this is the next best thing. And so it's interesting that this one problem, by adding more and more information into it, can go from incredibly hard to practically solvable. Just by putting in more structure into the problem. This is something that I think is a good lesson to take away from this class in general. Right? That a lot of times, the key to solving a problem is to put in the right structure into it that you can then exploit to get a better answer. And if that structure captures what you're modeling, all the better. So problems in Euclidean spaces are easier than problems in general spaces. Problems on a tree are easier than problems on a graph, and so on and so on. So looking for the structure that your problem might have hidden inside it that you didn't realize is actually helpful to get better answers. So what I want to do with the time we have left today is do one quick example of how you might go about getting a bound like this. Take a very simple problem where you can see this happen. For TSP, it's a little bit complicated. And interestingly enough, in almost all cases, there are two techniques that show up. Dynamic programming and discretization. Those are the twin tools that show up whenever you see polynomial time approximation cubes. This TSP uses both of them. It basically, what it does at a very high level, it says, oh, I have a bunch of points in the plane, and I want to find a good tour between them. I divide up the plane into grids. I decide to only allow paths in and out of a grid at specific locations, carefully chosen. And then I try to route a path that only goes through these portals. And show that this is a reasonable answer to my problem. Now, this is I've basically compressed many pages of discussion of exactly how this works. But it's ultimately a dynamic program with discretization. So I want to show you another problem now where simple discretization actually allows you to get these kinds of arbitrary bounds. Just to get a flavor of how these things work. And the problem we're going to look at is actually a relatively, not a very hard problem. Let's call it the following. So the minimum closing ball problem is defined as follows. I give you a bunch of points in a metric space. Okay. So there's some distance function. And I want to find some point C, which could be one of these points or not, such that the distance from the center to all these points is less than equal to R. And why it's called minimum closing ball, and R is minimized. And the way to picture this is that I have my points. And I want to find a center and a radius so my ball fits on these points. It's my terrible circle. Okay? So you want to find the tightest ball that fits all the points. The minimum enclosing ball. Okay? This is the problem. So first I'm going to give you a very simple two approximation. Okay, and the algorithm is so simple. I'll just write it right here. Step 1, pick a point. So let's say all I want to do is find R for now. Once you find R, you can find the center. Just pick a point, find its furthest neighbor. So pick a point P, find its furthest neighbor Q, set R equal to the distance of P to Q. That's it. And let P be the center. And set C is equal to. Done. So take any point in linear time, find its furthest neighbor just by scanning the other points and say that's my answer. Okay? So I claim that this answer, the center P and the radius R, is a 2 approximation. In other words, the radius I get is within a factor 2 of the optimal radius. Yes?
And what do you call it later?
Oh, sorry. What I mean is measure the distance to any other point and take the point minimum, take the point that's furthest away from it. So it's furthest neighbor means any other points in our sorry, in the set. Right, so for example, in this case, I might decide to pick this point as my P, and I will look around and find its furthest neighbor, which will be that. And the ball I will get will look something like this. I can even draw the whole thing now. So clearly this ball is not a good ball. It's worse than the optimal solution. But I'm saying it's not too bad. It's within a factor 2. And maybe you can start beginning to see why this might be a factor 2 and not worse than that. You don't have any thoughts on why that might be?
Yes, because it might lie on the circumference.
So that's like in your mind is the worst case scenario, right? The point you pick happens to be on the boundary of the true ball. And so it has to pick something that's on the other end. And so it kind of doubles. That's a very good intuition, right? That's kind of where it's coming from. How do we convert that into a proof is the question. Because this is where roughly the right argument is. So the way to prove this is to look at the optimal solution. Let's flip around, right? So let's look at the optimal solution. So there's some kind of optimal ball somewhere. And there's some kind of center. And let's look at the 2 points we picked. Right? We don't know where they are, but they're somewhere. So maybe P was here. And maybe Q was here. Again, there's somewhere in this ball, right? They have to be in this ball because the optimal solution is a feasible solution. So what can we say about this? Let's look at these 3 distances. Now, this is the optimal radius. This is the optimal radius. What can we say about the distance from P to Q? Yes?
Less than
Because?
triangular.
Very good. PQ is less than or equal to 2R, R star, the optimal solution. But what did we just say? We said PQ is going to be the radius of our ball. Right? So clearly, the radius of our ball is less than twice the optimal radius. Great. We're done. We got 2 approximation. But is our ball a valid ball? Will our ball actually contain all the points? Yes, because we took a point into its furthest neighbor. Every other point has to be in this ball because I picked the furthest neighbor. So we've got a ball, it's a valid ball, it contains all the points, and the radius of this ball is less than twice the radius of the optimal solution. It's trivial. Well, not trivial, but it's easy enough. Now that we know how to work with the triangle inequality, we can see this. But suppose we want to do better. Can we add more structure to the problem and make this better? So we know one way to add structure to say, well, these are not points in an arbitrary metric space, they're on the plane. So let's say we actually have points on the plane. Right? And I now want to find the minimum closing ball for points on the plane, and I want to get a better than 2 approximation because I hope that because I'm in the plane using Euclidean distance, I can do better. Here's what I can do. And this is a trick that shows up time and again in these kinds of p-tasks where you want to get very good approximations. Step 1, find a 2 approximation. Well, we just saw how to do that. We just take any point, take its furthest neighbor, we get a 2 approximation. Okay? Let's say this gives us a value r. Okay? Okay, now what? Now what we do is set delta, it's going to be a small number, to be equal to epsilon times r over 2 square root of 2. You'll see why in a second. And now what I'm going to do is, I'm going to make a grid. I'm going to discretize my space. Okay? Such that the length is delta. Okay? So what have I done? I've discretized the plane, at least the region around my points, not of course the whole infinite plane, where the grid cell resolution is this number here, which is a tiny fraction of the 2 approximation that I got before. Okay? Okay. Now what I do is, I identify the grid cells that contain actual points. Okay? And I replace these grid cells by a single point in the center. Okay? Now I throw away the grid. Throw away the original points. Only keep these special points. Okay? Do brute force to find the best solution for this. There are different algorithms for doing this, and I'll tell you about one. But just do something very wasteful and expensive. I claim that this gives us a good approximation to the truth. So, why is that? So first of all, how many such special points am I going to produce? The key insight here is that we know that a single ball of radius something like r covers all these points. There's one big ball of radius r that covers these points. Okay? We now broke up our grid cells into grids of this size. So a little bit of calculation will show you that something like 1 over epsilon squared grid cells will be sufficient to cover that whole ball. Think of the whole ball this way. So if you draw the whole ball out, this is of length 2r, this is of length 2r, right? We had these grid cells, this was epsilon r over 2 square root 2, and so on. How many things are you going to have? Well, you're going to have 2r divided by epsilon r divided by 2 square root of 2, which is equal to 4 square root of 2 divided by epsilon. Things on this side. Similarly, you have that many things on this side. The total number of grid cells is equal to in other words, the number of grid cells we produce is a constant. It does not depend on the number of points in my input. What we have just computed is something called a sketch or a coset. it's a reduced representation of the input that is very, very, very small. It's of constant size. But that's no good to us unless it's also a high quality reduction of the input. I can always reduce the input by throwing everything out. It's not very good. I want this to not only be small, but of high quality. Question is, why is it of high quality? The insight is the following. Let's look at any particular grid cell. Let's zoom up this grid cell. Okay? This is one grid cell. And it had some points in it. Yes? Okay. It had some points in it, and we replaced them all by one point in the middle here. Right? And we computed some ball on this. So let's say our ball actually was, this was a ball it was curving out like this. Right? Now this is bad. This ball doesn't actually contain a point it's supposed to contain. This is terrible. But how far is this point from this ball? What's the worst case scenario? The worst case scenario is this point is back here. What is this distance? If this is of side delta, this is delta divided by square root of 2. Right? Diagonal is delta times square root of 2. Half of that is delta divided by square root of 2. Right? What is delta? That's equal to epsilon times r divided by 4. Because there are 2 square root of 2 times 1. In other words, if you look at the ball we produce, right, increasing it by an epsilon r over 4 amount will cover all the original points. Okay. But we know that r over 2 is less than or equal to opt. So epsilon r over 4 is less than or equal to epsilon times opt over 2. Okay? So in other words, the solution that we produce for those gridded points, if we expand it by epsilon times opt over 2, we get a solution that covers all the points. And therefore, the cost of the solution after inflating it is less than or equal to opt plus epsilon times opt over 2, which I'm going to just sort of roughly say is something like 1 plus epsilon times opt. So this is how we get solutions that are within an arbitrary factor. Notice that we need to know what epsilon was before we ran the algorithm. Based on the value of epsilon, we chose a different gridding. The smaller epsilon is, the finer gridding we do. And this is, in fact, a rendition of a very natural heuristic. You have a problem, you want to solve it, you discretize it. And you do something on the discrete set. And that's all this is saying to do. And a lot of p-tasks work just for this. You discretize and do something on the discrete set. Now, I didn't tell you what I do with those discrete points. I said, okay, come up with an optimal solution. It turns out there are many different ways of getting an optimal answer. Some of them are expensive, some of them not. But the time it takes is a function only of the number of points. So in other words, our total running time is something like n plus some function of 1 over epsilon squared, because these are the number of grid cells I have to work with. So in this much time, I get an approximation that's 1 plus epsilon. And so as I make epsilon smaller, I get a better approximation, but I need more grid cells, so it takes more time to come up with the answer. And the notes have the running time bound, exact running time bound for doing this. So again, just to repeat, the way we can occasionally construct these very, very fine-grained approximations is when we can somehow discretize the problem and do something with the discretized version of the problem. Because that will either be of small size, so we can do brute force on it, we can do even exponential time things on it, it's still polynomial time in terms of n. Or we can be more clever, or we can do dynamic programming, and we can do a bunch of other things. I won't be spending too much more time on this right now. This is again a large topic that we could cover later. But I just want to give you a flavor of the different things. So what have we seen so far? We've seen things like TSP in general, there is no approximation ratio. We've seen set cover, which has a log n approximation ratio, but you can't do any better. We've seen vertex cover, which has 2. We've seen metric TSP, which has 1.5. And now we've seen minimum enclosing ball Euclidean, which has a 1 plus epsilon. So there's quite a wide range here, right? Going from almost exact to impossible. And if you think of all the NP-hard problems we've seen, they all look the same in terms of, well, they're all NP-hard. But in terms of where they lie here, they're all quite different from each other. So for example, a problem like find an independent set, maximum independent set in a graph. That's somewhere here. It's a very hard problem. A problem like compute a clustering in a graph, in a metric space. That's somewhere down here. You can get a 2 approximation pretty easy. Let's see, what else can we think about? Computing a minimum spanning tree is straightforward. That's of course polymer time. There are other versions that are not. There are various kinds of flow problems that sort of situate themselves here or there. Graph coloring, a problem that you may have heard of. Like how do you find the minimum number of colors required? Find the minimum number of colors you need to put on vertices of a graph so that no 2 adjacent vertices are the same color. You know that in a planar graph you can do this with 4 colors, but in a general graph it might take more. It turns out that even this is very hard, and this is something like here. The best known bound is something like it's like n to the 0.29 approximation, something very terrible. So all the NPR problems have situate themselves in this place. And so that gives you a more fine-grained, nuanced perspective on the relative hardness of these problems, which again is important. If you ever want to use any one of them or use them to model a situation you're dealing with, you should know which one to pick. Yes, they're all NP hard, but some are more NP hard than others. Some are worse than others. Okay? So, we're going to do one more lecture on approximations, but we're going to go to a different, we're going to sort of look at, so what we've seen in all these questions, right, is that you have very specific tools you build to find these lower bounds, and you have very specific instructions to design an algorithm that relates to lower bounds. And every problem is different. You got to think through it in its own way. For vertex cover, you do something. For TSP, you do something. For minimum closing ball, you have to do something. They're all very different. And this, of course, is annoying because we're computer scientists. We want a general procedure that works for everything. And next lecture, we will talk about linear programming, which is in fact, among other things, it's very important in general, but among other things, gives you a generic way to get approximations for any kind of NPR problem. And so we'll talk about it next time. So today is the 11th, 13th. Then we have basically 3 more lectures after that. So you have 18th, 20th, and 25th. Once we finish with linear programming, I don't have something I absolutely need to cover. So I often will do these kind of random one-off lectures, which will not be at the final, but just for fun, on random topics in algorithms that you may have heard about and you might want to know more about. So I'll post a forum question today. I'll throw out some things I've talked about in the past, but obviously, I'd like to have something new if you have something in mind. So if you've been hearing about things outside, in the world, things that relate to algorithms, you go, it'd be nice to know something more about blah, right? Post a comment in the forum, and if I can put together a lecture on that topic in that time, if I can pretend that I know something about it in that time, I will attempt to show you that I pretend that I think I know something. But I've covered, things like I've covered a bit of algorithmic game theory, origami, how to do paper folding, what's the algorithmic component of paper folding, a bit of quantum stuff, things like interactive proofs, zero knowledge proofs, and what that means, and all kinds of weird stuff like this. A bit of cryptography. These are all topics I know a little bit about, not a lot, but enough to be dangerous in the lecture. So think about it. These are just an opportunity just to have some fun topics. The class is almost winding down. And let me know what you think. Okay? All right. So I will see you on Thursday.